The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Hello, good morning everybody. I welcome everybody to the ACI special session titled UHPC Innovations in Durability and Resiliency. So you see here in a short overview we have 5 presentations today. We will start off with Dr. Graybeal from the Federal Highway Administration talking about the material properties in terms of durability of UHPC and the difference to normal concrete. Then we have 2 presentations by Vic Perry. It's the second and the fourth one, providing us information of practical application of UHPC and seeing there the durability of this material. Then we are being presented research results from the University Politecnico di Milano, and at the end we will hear some research effort and developments from the U.S. Army Corps engineers. I would like to welcome the first presenter, Dr. Benjamin Graybeal. He is the manager of the Structural Concrete Research Program at the Federal Highway Administration. Welcome, Dr. Graybeal, to the session.
It's a pleasure to be here this morning, and I'm glad that everybody stuck around till Wednesday and got up early to come hear a little more about UHPC. So durability. I guess it's good to talk about durability. It's been a while since I've had the chance to talk about durability with UHPC, although I do talk about UHPC quite a lot. It's probably the overlooked property. With UHPC, it is ultra-high performance concrete. It's not ultra-high strength concrete. It's not ultra-high ductility concrete. It is ultra-high performance concrete. So there are a lot of very impressive durability properties, and that is one of the key things we can key on when we're looking at applications for UHPC. So I lead structural concrete research for Federal Highway, and one of our research focal areas right now, and really for the past decade or so, has been on UHPC and how we can best make it appropriate for addressing some of our needs in the highway transportation sector. So UHPC. So the French recently published a design guide for UHPC, and in that design guide, it's not just. Am I not loud enough?
No.
Should I wander? Okay, I'll stand over here. Thank you. So they recently published a design guide on UHPC, and it's got chapters on structural design. It also has talk about sustainability and some talk about durability. And chapter 3 is about durability, and it's got this statement in there. And I think it's pretty important to recognize this, because this is really what's fundamentally different about UHPC as compared to conventional concretes. And it basically says that the durability is very good, and it would project very long life cycles for structures, and it's going to be explained by their particular porous structure characterized by an absence of capillary porosity and interconnected porosity on a very small scale. So not all durability, but most durability has to do with ingress of some liquid, probably carrying some sort of contaminant. And so if the water can't get in, basically, then your durability is probably going to be a whole lot better. And so the difference between conventional concrete and UHPC is the lack of that capillary pore structure, and thus your performance gets to be a lot better. A little more background. Federal Highway, we recently published a state-of-the-art report on UHPC, and it's got chapters on lots of different things. And I brought a couple copies, and I don't want to carry it back to Washington. So somebody's going to get these before we're done here. Published back in June. And it talks about a lot of things: mixed designs, material properties, design guides, deployments, and also durability. So I will be speaking to some of the information in there, and it contains obviously lots of information beyond what we've done at Federal Highway. There's more than 300 references, a 600-item bibliography there. But what I'm mostly going to be talking about in this presentation is a lot of information that came out of this report. This was published in 2006. It's work we did in 2003, 4, 5 time frame. looking at characterizing a UHPC, including lots of durability tests. A paper that I published in the Journal of Materials and Civil Engineering on the durability of UHPC. That was back in 2007. A report that we published earlier this year on grout material characterization. We're looking at using UHPCs as grouts in field cast connections between prefabricated elements. And we looked at lots of different grouts and we were comparing their performance, both mechanically as well as from a durability standpoint. So I'm going to talk a little bit about this. So, in terms of some of the results, the first one I'll talk about is rapid chloride. In the bridge sector, in the highway sector, we talk a lot about the rapid chloride test, probably because it's easy, not because it's perfect. But it's C1202, and you basically pass an electrical charge through a slice of concrete, a 2-inch thick slice, 4-inch diameter, and you see how much current passes. It's an indirect measure of the charge passing ability, which can give you an indication of the resistance to chloride permeation. Values down there at the bottom you can see in terms of a rating from negligible up to very high. Conventional concretes that you might run into these days are probably in the moderate range. Sometimes we specify things that are in the low range. You can see the values there with some UHPC tests that were done a little longer ago and more recently. And it does depend on how you cure the material, but your values are in the very low to negligible range. So pretty good performance on the UHPC. Other people have run similar tests. These are tests that we did at Federal Highway. If I can real quickly pull this out. Also on this topic of sort of permeability and more actually permeation, people have done the type of permeability tests where you actually pond something and you check the permeability. You look at diffusion coefficients and the numbers for UHPC are very low. There might be in the range of 2 times 10 to the minus 13th meters squared per second. And then people have also done work with under pressure, so up to more than 200 psi of sustained pressure on a sample of UHPC to see how far the liquid would permeate in. And in that particular set of tests by Gao, the water permeated in around 1/10 of an inch. So very minimal permeation under pretty high pressure, water pressure into the UHPC. So again, it goes back to that point of if the water can't get in, then your durability is probably going to be pretty good. Freeze-thaw resistance. Traditional freeze-thaw test that's done in the U.S. is ASTM C666. You run it for 300 cycles. You check the resonant frequency. So there's some data from some UHPC, and you can see it kind of stays right there. Its resonant frequency doesn't really change. And that's what you want. Frequently, a conventional concrete that doesn't have a good air void structure would fail well before the completion of 300 cycles. But in this set of tests, what we did was we said 300 wasn't enough. Let's go to 600. Let's see if something happens, and we did. And we still stayed right around 100 for our relative dynamic modulus on the resonant frequency. So very good performance. We really didn't see any degradation with this UHPC. Some more recent tests and some older tests that we've run on some different curing conditions, and you can see the numbers all stay around 100%. The one there where it went up to 112%, if you don't saturate the specimen before you start the test, you can actually see an increase in freeze-thaw resistance, or at least an apparent increase. It's not really getting better because of the freezing. It's getting better because some water's getting in and hydrating some of the unhydrated cement inside the matrix. So your stiffness actually goes up a little bit, so your dynamic modulus goes up. Scaling resistance, ASTM C672, are some tests we ran on a slab of UHPC. You can see it doesn't, well, the one on the right's wet as compared to dry on the left. But other than that, it doesn't look much different. This is a qualitative test where you look at the surface condition, and we basically saw no scaling after the completion of the test. So good performance there. Some other people have looked at this, run some similar tests, as well as some tests that are more standard in Europe. I'll point out that Schmidt et al. Ran a test on scaling, and it's more of a quantitative test, and they looked at the volume that was scaled, and it was less than 10% of the acceptable limit for a concrete after the completion of the test. It was about 7% of the acceptable limit. So very good performance on a German test for scaling. Abrasion resistance. This is a little different than the water permeation type tests. This is looking at the abrasion resistance of the surface. ASTM C944 is one abrasion test that's out there. This is one we ran at Federal Highway, and we found pretty good results. Changes a little depending on the curing treatment that you apply, but really very little abrasion. And I'll point out that this particular UHPC is not one that has an extra hard aggregate and thus is designed for exceptional abrasion resistance. This is just sort of a run-of-the-mill available UHPC and how it performed in an abrasion resistance test. I guess one more, alkali silica reaction. There was a question out there of what happens under ASR type conditions. And we ran these tests, and for ASTM C1260, if you're less than 0.1% expansion, it's considered innocuous, and we got numbers that are basically 0. So it wasn't expanding under these very aggressive conditions that are under C1260, where it's a very aggressive solution in a elevated temperature. So good performance there. So the durability is pretty good. I'll point out there's been work on some other topics. There's been work on fire resistance of UHPC, and it can be good. You do have to do some work to ensure your fiber content is appropriate to give you the right fire performance. You might mix your fibers, a PVA type fiber maybe, or a plastic type fiber with steel fibers. Other work's been done on marine exposure in severe conditions. For those familiar with Treat Island, Maine, it's freezing and thawing in a tidal zone, and there's some UHPC samples that have been up there for more than 15 years and have been shown to perform very well in that aggressive environment. Sulfate resistance, some testing's been done on that, testing on carbonation. So there has been a good bit of work on durability of UHPC, and really the answer is that the durability seems to be very good under the sort of conditions that we normally expect that we would use concrete. So it's pretty good concrete. But what if it cracks? So a lot of the tests we run on concrete, we do those tests on sort of the bulk testing of the material. We look at the concrete between the cracks, and we know that concrete sometimes does crack. So there is a question of, so in UHPC, what if it cracks? How does that affect the durability? And so there's been less work on this topic, but there has been some that investigates what the performance might be if you move into a crack condition. We did a study at Federal Highway on combined environmental and structural loading. So we were basically cracking the UHPC, and we were applying structural loads also, and we were checking how the structural response changed under the aggressive condition. This is a report that was published in 2010 that is available, and I can certainly help anyone find any of these reports that I've talked about. Here's basically what we did in this test program. We had a beam. It was a 16-foot long beam that we applied 4-point loading, so there's a constant moment region there in the center. And you can see we're pushing down into a sponge of salt water, and this is that sponge of salt water. So it was a cyclic loading test. It ran for 6 months, and every 30 seconds or so, the actuators would engage. They'd push down the specimen until it squeezed the sponge, and the sponge squeezed the salt water up into the bottom flange of the beam. So that's what you can see here. This is when we just started the test, and so the water was starting to sort of, the salt water, very high concentration salt, I think 15% solution salt water. It's pushing up, and so we were wetting the bottom flange. Every cycle was beyond the cracking limit. So on the first cycle we ran, a series of very closely spaced cracks occurred, and then for 6 months we continued to push on the beam in that condition. So we were looking at, does our flexural resistance degrade if you're in an aggressive environment like that? So if you look here at this picture, you can see that here's some of these cracks, and you can see the salt seems to be migrating up the cracks, and that would appear that you might think, oh, well, that's not so good. We've got a steel fiber reinforced UHPC, and we've got salt in the cracks, and that could present some degradation. But what you need to also recognize is that cracks in UHPC are very tight. It's generally a strain hardening cementitious composite material, so you might have around 2% steel fibers in there to get that sort of tensile structural performance. And what you get with that is very closely spaced, very tight cracks. And I'll talk more about that in a second from another study that we did. So basically, you are seeing an indication of where the cracks are, but that doesn't mean the salt is completely through the cross-section on those cracks. That may mean that just on the very surface where the cracks are widest, because there's least restraint there, the salt water seems to be migrating up the edge of the cracks there. Throughout the 6 months of loading, we honestly expected we would see some degradation in the performance, but in our tests we didn't. The flexural performance remained the same throughout the entire time we ran the test. And after 6 months, we had to give up. We had other things we needed to test. But we took the specimen out because we thought, well, maybe there's been some local degradation. And so I'll go back. So this is the bottom flange of the beam. It's a 6-inch wide beam. So imagine you sort of cut off the bottom 1 inch of that beam in the constant moment region where you're pressing on that sponge. That's what we did. And then we took that 6-inch piece and we cut it into a 2-inch wide piece. So what you have is a 1-inch by 2-inch piece, cross-section here. And then sort of this stick here. And then we grabbed it and we pulled it. And we thought, okay, this is the most severely tested region. It had the highest tensile strains. It was right on that saltwater sponge. We thought, if you look at this real closely, you can see some of the lines where some of those cracks were. And we thought, okay, we must have somehow decreased the tensile response across those cracks. So let's pull on it and let's expect that it's going to fail where the fibers bridge those cracks. And we did. And we pulled on it, and the first time it broke right here, and it wasn't on one of those cracks. And the second time it broke right here, so we had this left. We pulled again, it broke here, and again, that wasn't on one of those cracks. And so the third time we had just this little chunk here in the middle left, and we basically took a router and we routed around an individual crack. We traced it all the way around, and we said we're going to reduce the cross-section at this crack, and we're going to really try to force it to fail there. And it did in sort of a tortuous manner, but it didn't follow the plane of the crack. And I'll show you that here in a second. So on that last one, on this failure here in the center where we routed around the crack, here's what the cross-section looks like if you look down at it. And this spot right here, this is a spot where the salt had gotten in a little bit. And so you can see it's a little bit whiter there. But the rest of this, well, there's a little spot right here also. But the rest of this, it actually failed elsewhere. So this gives us an indication that, at the very least, in a qualitative sense, we didn't seriously degrade the tensile capacity of the cross-section, even though we were under that aggressive environment for 6 months, combined with the structural load. So it's hard to make a definitive conclusion from this, but there's not an obvious Achilles heel here. It seems that the performance remains pretty good. So what I'll finish up with is this. This is one other study we did, and we were looking at crack widths in UHPC, and this is really why this works. If your cracks are really tight, it is still hard for the water to get in. Now, it's easier than if it's uncracked, but it's still kind of hard to get in. Published a paper at the Proceedings of FIB in 2010. This was the FIB that was in Washington, D.C. And we were looking at flexural response of lightly reinforced UHPC beams, but part of that was looking at crack widths in UHPC. This is basically the same test setup as the test I was just talking about. We had a 6-inch wide, 16-foot long beam and 4-point bending. And we were loading those to failure, and we were monitoring the crack widths during the test. So we periodically stopped during the test, and we counted up the cracks and measured how wide they were. And basically what we found was in 2% steel fiber reinforced UHPC, our mean crack widths were about 0.006 millimeters. In 1% steel fiber reinforced UHPC, it's about 0.0017 millimeters, and that's pretty small. Take a microscope at 200x. This is what one of those cracks would look like. Blow that up to 800x. Here's what it looks like. So this is one that's 0.003 millimeters wide. Just to give you a sense, in normal concrete, you might have cracks that are around 1/10 of a millimeter wide. So the cracks are very, very tight. And that obviously makes it difficult for those aggressive things to get inside the UHPC. All right, so that's the quick coverage of durability and kind of what I know about durability of UHPC. And I think I'll end there, but I'll be happy to take any questions if we've got time.
Thank you, Ben, for the excellent presentation.
Ben, I have a question for you regarding that beam that you had in cyclic loading over the sponge that was saturated with salt water. I noticed that on the cut face of your specimen that you took after the fact, there were rust stains. Were those rust stains there when you cut it, or did they just appear after it had been exposed to air?
Well, it was so. I guess there's two answers to that. It was actually exposed to air from the beginning, because it would push down into the sponge, and then the sponge would push water up. But as soon as you release, the air sort of sucks back in. So the air was there from the beginning. Now, if you have a steel fiber reinforced UHPC type material, you will get surface staining if you're in a very aggressive environment. Now that surface staining doesn't really progress into the interior, but the fibers that are very close to the surface, they'll corrode. So that can be an aesthetic issue, but it's not really considered to be more than an aesthetic issue. So what you saw there is what, in a very aggressive environment, what your surface might end up looking like.
Okay, yeah, because I mean, it looked like where it had fractured, it looked like there was no evidence at all.
Exactly. Right, and so we looked at the fibers under a microscope to see if could we see some reduced section, or could we see anything, and we didn't see anything on the inside. But those fibers right at the surface, like just underneath the form, will corrode.
Well, I thought that was the cut face that was exposed, you know, when you had it sitting up, or was that the exposed face?
If we can.
You know, when you're.
Yeah, I know which one you're talking about. So this would have been the bottom face of the beam that was touching the sponge. That face you see right there. So.
I'm not sure you are involved, but is FHWA doing any fire resistance testing on ultra-high performance and compared to conventional concrete?
We have not. I haven't been involved in any. I'm aware of some. And traditionally what's done is that you can get better performance, but with fire you need to have a way for the water to get out as it turns into steam. And so the fact that UHPC has such low permeability, that could be an issue. You use some sort of, I guess you could say, a meltable fiber, and that allows some pathways or some expansion locations for that water, and then you can get better performance. Yeah.
Thank you very much.
You're welcome. And I've got 2 of these. Anybody want?